I will be talking today about long-term passive acoustic monitoring of unique vocal signatures of Turiops truncatus, bottlenose dolphins in Namibia. Okay, here we go. Which is part of the SWORD project, which I think you heard about yesterday. So my study site is in Namibia, where we've done a lot of work. This program was started in 2008, I believe. From local ecological knowledge, we believe the estimated range to be around 800 kilometers on the coastline, ranging from Moe Bay down to the south in Lüderitz. We've got published photographic data with resightings between Walvis Bay and Lüderitz. And then in the most recent work that I've done, I've seen acoustic recaptures of signature whistles between Cape Cross and Sandwich Harbor, which is around 400 kilometers. So as I said, we've done a lot of work there. We know, but all of this was done with boat-based surveys, mostly based around Walvis Bay. We know their distribution, we know certain hotspot areas, we know behavior, we know the seasonality, and different cohorts that have changed over the years, and an estimated population size from the last published data ending in 2012 of around 70 individuals. And then lots of other publications in terms of the repertoire, characteristics of the signature whistles, sexing of the individuals in the population, and then some kind of like fine scale unique behavioral strategy for foraging as well. My PhD is trying to move away from all of that, stay off the boat, stay on the computer, and do statistics using passive acoustic monitors. Historically, a lot of this work's been done either in captivity or with capture release events, which we don't really have the funding for or capability to do. What we do have the ability to do is put sound traps and hydrophones in the ocean and record dolphins for long periods of time and collect signature whistles to mark them and capture them and recapture them for various purposes, which I will get into. So I'm going to give a brief overview of a few of the results from all the chapters of my PhD that are completed so far. I'm going to skip a lot of the information and just give you the basics of methodology. The first chapter, we looked at kind of a fine scale analysis of how to deploy hydrophones. So we know, and you can see in the left map, Aphrodite Beach is a high use area, and we deployed 3 hydrophones there and then looked at detection rates between the different hydrophones and how those affected mark recapture models. Previously published work has said that you can hear or perceive signature whistles up to as much as 20 kilometers, but those, the northern and southern site is only separated by 1.5 kilometers, and there was differences between those sites. The results here to focus on are that the northwest site, just a kilometer and a half away, estimated a detection probability much higher than the southeast and southwest sites. I then implemented duty cycling in a post hoc way and found out that for this population, a 66% cycle is the most effective way to capture signature whistles and extend your deployment time, giving you the same results as 100% almost, if not better, at least for capture probability. And just to caveat that, this will change for population, this will change for study site. So even with these results, it's really important to know what you're looking for, what your question is. And this will, in another site where these guys use frequently, this might be different. The next study, so signature whistles are vocally, are dependent on vocal production behavior. So they do produce a large amount of signature whistles. I think I skipped over a slide. So a signature whistle is a unique marking that a dolphin develops at birth. And these are learned signals that they develop through a process called vocal production learning from other members of the population. Through our previous work, we have identified 80 signature whistles in the population. But then what I was interested in looking at is how the vocal production behavior, knowing the age classes, the group size, the sexes, the association levels in the group, whereas with the hydrophone deployments where you're not there, you have none of that information, how that kind of affects the production of signature whistle types, and then how that will affect the population modeling moving forward. So we deployed a hydrophone, our office is there, residence is there, and then these dolphins use this lagoon quite frequently, so every time they would come in, we would go out and photograph them, and they would also we'd be recording them at the same time. With these results, I was able to look at production rates of signature whistles and found that with more males, more adults, and more calves, let me back up a second. So these two plots and models are basically the same thing, but inverted. One is a true production rate, where it's just the number of signature whistles over the duration of the event. The other, I modeled interwhistle intervals. So it's effectively an inverse signature whistle. So the longer the interval between whistles, the higher the production rate. And you can see that more males, more adults, more calves lead to more production of signature whistles. And larger group sizes leads to a smaller production rate, but you do get more signature whistles, obviously, because there's more members of the population in that area. So this all kind of is building and feeding into the kind of like end goal of my PhD, which is to use spatially explicit capture-recapture and mark recapture models to estimate abundance and track the population. And you can see in a basic mark recapture model, the acoustic data and the photo data gave the very similar estimates for detectability over the 14 encounters. So the final study I'm going to talk about is we deployed a large-scale array, 6 hydrophones, across 400 kilometers of the Namibian coastline for 3 months. This is only 2 weeks of the data. And in that, we were able to capture 35 signature whistle types, all of which were seen at least twice or recaptured at least once at another site along the coastline. From this data, I was able to trace them, and I used a technology that was developed in MATLAB in 2004. And I'd really like to learn some AI and things to speed this process up. The 2 weeks of data took 35 days to process and categorize. And what it does is compares, how do you get back? Can you play that on your side? Yeah. So I've traced the contours, and then it's a unsupervised neural network that matches and recategorizes each contour together, forming distinct groups of beautifully matched contours. And effectively each one of those is an individual. You have to, and this is the slide I skipped, to identify signature whistles in a population from wild recordings as opposed to in an aquarium or using suction cup tags where you know the individual who is producing that whistle. There was a method developed by Vincent Yannick and Stephanie King called SIG-ID, which is a bout analysis approach, of which there's 2 criteria. You need at least 4 whistles that look highly similar, and 3 of those 4 whistles must occur within 10 seconds of the previous whistle. So the top 2 categories passed, the bottom 3 failed. The first one, which is a signature whistle on the left, but there was only 1 of that type within that time period. The second category, you can see those shapes don't match. It wasn't able to converge in that group. And then the fourth one, which does look like it matches the temporal patterning, was not successful. So none of those whistles were within 10 seconds of the previous whistle. From this data, I was able to run spatially explicit capture-recapture models. Don't worry about the models. The important information to note here is that with 2 weeks of data, I was able to get an estimated abundance of 72 individuals in the population compared to 4 years of photographic work, which also was 54 to 76 individuals. And then more recently, Emma Longden published a paper with 6 months of data, which gave a similar estimate. So, story being, this is going to be a really effective method. I think there's implications to look at in terms of the behavior in vocal production and how to deploy these hydrophones most effectively. Obviously, buying more hydrophones is the easy answer, but not everyone can afford those. Things like audio moss or wildlife acoustics, which make great devices, also don't have like the capacity or to do kind of large-scale coastal studies of entire populations like sound traps do, which are wildly expensive. This also, you can estimate density. Right now, and I'm just kind of working on this, 1 dolphin per hectare, not a very useful number. So I'd like to, you can split that up and look for individual hotspots, and look at fine-scale movement patterns, site fidelity, social networks, and then even like rates of fission fusion changes in their social structure over time. Using passive acoustics, which is a pretty cool idea in my opinion. I'd also love to say, so this is the SWORD team. Guy, one of his favorite expressions was ba, which is a Brazilian phrase. That's a result. And then thanks to Tess, Simon, myself, and Sasha, and all the funders and collaborators that we've worked with.
Thank you so much for your talk, Jack. Do we have any questions from the audience? All right, I think we have a question from the online people.
Thank you so much, Jack. The question is, what was your definition for long-term monitoring? How long did you monitor the population for?
Fun question. That's a fun question. I spent an entire year tracing whistles and whined and moaned and about 3 months of data. Then you hear people who have data sets that are 3 years, 10 years, 100 hydrophones. So long's a relative word. I think I was able to get an effective answer in 2 weeks. So it really depends on the study question and the population and the species. I know like Sasha, who's talking tomorrow, is doing a similar work on the humpback dolphin, much harder to detect. So it's more about knowing your population, which I had the benefit of a lot of background work done by other people to kind of inform me on that effect, but yeah.
Thank you once again, Jack.